Okay. Yeah. Good morning again. Today we are going to start the third part of the course in which we are going to utilize the graphics hardware that has been developed in the last 20 years or so. We are going to take a look at the GPU architecture, graphics processor unit, and we are going to learn a new library to use these graphics hardware named OpenGL. And OpenGL will not be sufficient on its own to open up a window. So for window management and stuff, we are going to also use a library, but we are not going to use it in full capacity. So it's going to be just basic operations. We are going to provide you lots of examples, lots of templates that you can work on. I'm going to share with you some examples. And the most important thing to be able to write code in OpenGL and develop upon these examples is to have yourself a development environment in which you can compile and run OpenGL programs. So that will be whether it's your laptop and also on INEC machines in our department. These libraries are already installed, so you can also use them on our department's machine. But if you want to set up your own system on your own personal computer, you'll have to spend some time to install these libraries. We're going to share with you some resources in this regard, some links. There is a post by one of your friends, students last year, for example, how to run GLFW on Ubuntu. I'm going to share this in OptiClass in the announcements. So how he was able to manage to run VS Code with debugging option with OpenGL. So the libraries basically we will be using are Glue and GLFW, and how you can install those. I mean, he provided a nice walkthrough, a README file to start working on these. I'm going to also show you. So I got my desktop here recently updated, so I don't actually have a working environment for OpenGL compiling and running OpenGL programs either on my machine. So I'm going to show you two options. First, to develop on Windows machines, how we can, I mean, there are basically multiple solutions to have these OpenGL compiling and running OpenGL programs on your machine. I'm going to show you one of those paths. One on Windows. Actually, I'm going to show you two paths. One directly natively on Windows. The other is by using WSL, Windows subsystem on Linux. So this is like a native Linux shell here that is running on my Windows. I have WSL1 running here. WSL2 I think directly supports also I think in Windows 11 you don't even need an X server. So OpenGL programs are like graphics programs, so they're not going to be command line programs. You'll have to they'll have to talk with the Windows system. So either I mean, the reason I don't have, so I have a Windows 10 here, I didn't upgrade it to Windows 11 yet, and I had problems with WSL2 because it's using the same network, I mean, it's really native, so my firewall was having problems with WSL2, so that's why I downgraded to WSL1. But I'm going to show you how with WSL1 we can run an X, so this one is VCX server. So I installed a program called an X server that runs on Windows. How by using this one you can actually manage to run OpenGL programs within your WSL2. But maybe we will not need that. I mean, if you already have Ubuntu installed on your personal machines, it will be, you will not need to deal with these things. Okay, just follow the README provided by your friend last year. I'm going to share this on OptiClass, as I said. and hopefully it will help you to set up your environment. So that's really critical. For the third assignment, you will be writing an OpenGL program, and you'll see that all these, we have up to now, we have seen the theory behind. I mean, it was as an introductory computer graphics course. We gave you all the background and theory that will allow you to write your own libraries that's for rendering. You're in the second assignment, you're writing a software rasterizer, which actually people did early days of computer graphics, where we didn't have these graphics cards. We have seen ray tracing, so all the theory part is complete. Now the last part of this course, we are going to talk about how we can actually make use of these high-end graphics acceleration, hardware acceleration that is available to us by our graphics processor units. Okay, so let's go ahead and start with the slides. Then I'm going to show you some examples. I have this GLFW examples here. Let me extract it here. I'm going to also put them on AutoClass. Okay, so I have some example programs that I had written earlier. A very simple test program, a texture mapping example, a terrain visibility, and depth as texture. These are a little bit advanced programs. I may also show you. I also have Marty and the Rocks GLFW. I'm going to show you that one as well. I'm going to find it. But let's go ahead and start, and when we start talking about GLFW, and after we finish these slides, I'm going to show you these examples in real time, how we compile and execute those. All right, so by the way, if you have any questions about anything, maybe off topic, maybe about the second assignment. By the way, the depth buffer algorithm is not going to be a bonus part in second assignment. It's not going to be because we thought changing the assignment's description. I mean, some students may think that we're giving some extra work, because although it's bonus, everybody's going to try to do that. So we didn't want to increase your workload on the second assignment, although it's something not that difficult, but we didn't want to change the specification, so it's not going to be given as a bonus. So you will not need to do a depth buffer algorithm at all in the second assignment. Anyway, I was saying, if you have any questions about anything, feel free to write in the chat box, or just unmute yourself and speak up if you want to. Okay, so let's go ahead and start these slides. There's the first uploaded slides, I also updated them a little bit. A couple of slides were edited, so the updated ones are version 2 on AutoClass. All right, so let me zoom in a little bit. All right. Right. Okay, so this is the repetition of what I just said. We have seen the theory, the algorithms behind rendering, algorithms, hardware, but we didn't talk about the modern graphics applications which use OpenGL and hardware acceleration. So these days, if you're going to develop a game or a simulation or any graphics application, you really need to use either OpenGL or DirectX or Metal. Up until recently, Apple OS X was also using OpenGL, or Vulkan, but now they're changed to a different API, but they're all very similar. They directly talk with the graphics processor unit by sending geometry. So it's basically, we send data to the GPU in one shot at the beginning of the application, and the GPU has the capability to, it has its own memory, and it has these forward rendering pipeline implemented in it by default, so it can render lots of triangles, millions of triangles, 60 times per second. So it's really, we are going to see how it does that. Yeah, this OpenGL is like actually a standard, and it's a library obviously, but installing OpenGL is a little bit different. You don't install this library separately. Actually, it's the library that if you install a driver for your graphics card or update your drivers for your graphics card, basically those are the OpenGL libraries. But these libraries, since they're just functions that are pre-compiled, in order to have a development environment, you need those header files and everything. So that's something else. And also to tap in those advanced functions, you need an API, application programming interface, to write a program to which is going to have these list of functions that are available to you that you can use. So this is what we're going to be doing in this last part of the course. There are other APIs that can talk with the graphics hardware, like Direct3D by Microsoft, or other APIs, but the most common one is OpenGL. All these game engines, like Unity, Unreal Engine, they are actually built on OpenGL, so they are using these in the background. So, for example, Unity, although it provides you lots of functions that are very easy, like the physics engine or certain shaders already implemented. Certain things are really fast and easy to code in game engines or graphics engines like Unity, but sometimes they can be very heavyweight. In order to provide all these functionality in a generic manner, they may include lots of functions which are not necessary actually if you're going to have a very simple application. So knowing OpenGL on your own and writing your native OpenGL application sometimes may be more efficient than using Unity directly. Okay, it may be more time consuming, but it will give you more power. Certain things you cannot do in Unity, it's maybe possible to do that by using OpenGL and writing code in for the graphics hardware using the GLSL language. So the graphics hardware basically is a set of components which implements the forward rendering pipeline. So we're saying it implements a forward rendering pipeline, but at this point you may ask, we have these RTX chips, right? I mean, RTX cards, which is graphics cards for ray tracing. How do they do not basically implement the forward rendering pipeline, they implement the ray tracing. How are those functions called? I have no idea actually. I don't know how the RTX API works, how applications that you develop, how you can do ray tracing on a graphics hardware. I don't know that myself, so I have to do some digging and reading to learn how it's done. But for this course at this moment, I don't know how that's done. Okay, so but the general, it's a new technology. The classic way of using graphics cards is they implement the forward rendering pipelines, and this is what we are going to focus on this course. But if you're interested, probably it's an advanced ray tracing course. I don't know whether Ozuca touches on that graphics accelerated ray tracing, these RTX cards, how they work, but they should have some documentation and API to be able to use them. So modern GPUs are programmable means that they have a really, this is really interesting. So when you write a program, all this operating system, I mean this Windows, it's running on your CPU. It may be quad core, there may be 16 cores, but it's still that CPU. All this operating system is running on the CPU. Your memory, it's CPU. So GPUs have a separate processing power on their own, and but the programs we write here, when you write a C program here, you cannot access the memory or the instructions. You cannot give instructions directly from a C program to GPU. So the way GPUs are programmable are that you can actually at runtime, when you have a program on the CPU, you can give instructions in such a way that take this code, upload it onto the GPU, compile it, link it, and start executing this code. You can say, you can make, these instructions may be given by the CPU side, and it's possible to write these code and install, not install, but at runtime dynamically, you can load programs onto GPU, compile them on the GPU, link them, and say, okay, now execute this piece of code on the GPU. You can do that, but the access is, as I said, indirect. So usually the terms host and client, so it's kind of a host-client architecture where I usually confuse these things. If you already know, please let me know. Either the CPU or the GPU, one of them is called a host, the other is client. Yeah, I think the GPU is the host and our CPU is the client, but I'm not sure. But there's a host client kind of architecture between. So there's a message passing and communication that has to go on between the host and GPU. And we are going to see examples on how we can do these things. And GPUs are, their architecture are considerably different than CPUs. They are massively parallel. For example, let me look at my graphics card here. NVIDIA control panel. So I have an NVIDIA GTX 1660 Super. I don't know what this is, but this is my driver version. If you look at system information, okay, we are going to see that it has 1400, so 1408. So if you, let me start annotate, if you look at this part, it has this many cores. So it's like having a CPU of 1400 cores. So it's massively parallel, but it's not like CPUs. Each of these cores are much smaller than what the CPU cores provide. So it's like, consider it's like these are like ants, small ants. You have 1400 ants, and the CPUs are like there are elephants. They are large. They can do massive tasks. So each core in your CPU, it's like you have 4 elephants, but on the other hand, you have here 1400 ants. For certain tasks, these small ants, although they are small, they can be more suited to perform certain tasks if those tasks are easily parallelizable. But certain tasks are better done on the CPU if they need this heavy lifting. So, and in terms of, if you think them as like in the army structure, your CPUs are tanks and your CUDA cores are like foot soldiers. So certain things can be done better with 1400 soldiers than just 2 tanks. Okay, so it's really application specific. It doesn't mean that these 1400 cores are really always better than CPUs. It's not always like that. Depending on the application, depending on how parallelizable it is, these cores are they are massively parallel things. Okay, so here this power actually is also used by general purpose non-graphics applications. Hence we have the term general purpose GPU, GPU. And you already know probably this. For example, for Bitcoin mining, people are buying graphics cards. Why? Because they're using this, they're trying to find this hashed value by trying lots of things. Actually, it's just a waste of Earth's resources, to tell you the truth. I mean, we're just mining something virtual, and it's just requiring lots of electricity, which means electricity at the end is really using Earth's resources. So it's not green at all. But that's basically what they're used for. You have graphics cards. These cores are used for some general purpose computing with this library. So this CUDA is that library that allows you to tap in to these cores and execute some general, not necessarily forward rendering pipeline types of calls. So it has different parameters, the graphics cards, dedicated video memory, 6 gigabytes, and shared system memory, 8 gigabytes. So different parameters here. Anyway, so let me continue with this. So they're massively parallel. We are going to see how this architecture is done, and they change continuously, mainly due to the demands of the video game industry. There are new specifications, new functionalities, new functions are available at each generation of these graphics cards. This ray tracing, for example, is something that is being recently made available. There are some big players in this industry like AMD, NVIDIA, Intel, Microsoft, Apple, Qualcomm. These are some of the companies that are that take their share in this graphics hardware market. So I'm going to show you a video. This is from I think it was an NVIDIA showcase. Many of you probably know the Mythbusters. So Mythbusters made this demonstration to show the difference between a CPU and GPU, how parallel GPUs may help. So it's a short video, about 2.5.
Alright, I introduced to you Leonardo. He may look like a skid-steer BattleBots platform with a paintball gun mounted on it.
Sorry. Let me run it again. GPU versus CPU.
Alright, I introduced to you Leonardo. He may look like a skid-steer BattleBots platform with a paintball gun mounted on his head, but in fact, at heart, he's a painter. And he's going to paint the picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. This paintball gun is an XY servo-driven bot that will readdress itself for each pixel that it has to lay on this canvas right here. In 3, 2, 1.
Yes. So this is how CPU does things. So sequential, serial manner. Now the GPU. You see the NVIDIA logo there.
2,100 pounds, gallons, of air goes through these accumulators, out these valves, into all 1,100 of these tubes, which are all exactly the same length, into these tubes, in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
It's kind of like a parallel processor, or a GPU.
Alright. Armin!
Okay. GPU painting demonstration. And 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
I think we are going to also see it in slow motion. Yeah, let's see that again in slow-mo. So that's really impressive, and it was in 2008. Okay, so about 13 years ago, it was, as I said, a showcase for GPUs. Yeah, as a result of this performance, GPUs are also used in, as I said, many tasks other than computer graphics. This is called GPU, general purpose computing on the GPU. And there's a language, this CUDA, that the API is developed especially for general purpose graphics processor unit computing. And there is also languages like OpenGL supported by AMD, NVIDIA, and Intel. Which is also used for GPU. Like Many deep learning applications, they run on the GPU, image video processing, analyzing big data, machine learning, bioinformatics optimization. So they tap into the power of GPUs. So we are going to quickly go over the architecture just to give you some information. But as I said, these architectures are continuously developed, and some of them may be outdated quickly. So just give you this general overview of how it's different than CPUs. In their building blocks, they are similar to CPUs. And somewhat simpler than CPUs. They have some logic to decode the instruction to be performed. They have registers, ALUs, cache, memory. There is data parallelism and pipeline parallelism. What makes them parallel is they are, I told you this at the beginnings of the course, the SIMD architecture, single instruction, multiple data. Those matrices that, for example, we have a matrix, a 4x4 matrix, and we want to multiply 1 million vertices with this matrix. So into our data, the vertices, the vertex data is massively parallel. There are multiple data, but the instruction is the same. Multiply them with this single 4x4 matrix. So such an architecture, such a parallelism, single instruction, multiple data, the same instruction is applied to thousands of data elements at the same time. So there's a data pool. These may be our vertex buffer data, vertices, and there's some instruction pool, which gets, all of those are the same instructions that are applied on the same data. This works well for independent tasks. For example, our ray tracing, individual pixels, they are really independent from each other. They share some data, they share the same virtual scene, but when one pixel is running, when you're computing the color for one pixel, you can actually compute the color for another pixel independently from that. So, or when we're transforming a vertex, when you transform one vertex, you can transform the other vertex independently from the other. So these are all independent and nicely parallelizable task for us. If the task is the same but the data is different, so we can have, for example, if you're just going to divide each of these numbers by half, this is your data, and your pipeline is just one instruction long. So this is the pipeline on the left, and this is your data, and you can just do it in parallel, apply the same instruction to all of these data in parallel very fast. So GPUs have a larger number of arithmetic logic units, which we call these cores for data parallelism. Each of these cores, or a unit of these cores, may have a cache and some control mechanism on them. So they share certain things set in a hierarchical manner. Sets of them share certain things. There's a RAM, for example, a shared memory, which is shared by all the cores in an efficient manner. So this is a 4-core CPU we see here. These are the arithmetic logic units, 4 of them, and we have many of those on the GPU. So this was with a comparison between Intel i7 with this generation, and this is GTX 1060, which is, as you can see, more than 60 cores. The clock speed of the CPU is larger than an individual clock speed of the cores, and but the GPUs generally require more power, and the memory bandwidth is also really high on GPUs. If you look at the memory bandwidth, it is 200 gigabytes, whereas in this Intel i7 it's 25 gigabytes of bandwidth. So this, if you look at this overall architecture, there are different caches, different levels of caches, L1 cache, L2 cache. This is the frame buffer. They talk with the frame buffer. There's a thread processor. I don't know the details of these GPUs myself, so you don't need to memorize or understand it. Just know that it's really massively parallel with lots of cores, and it runs on this. We have the forward rendering pipeline, the OpenGL pipeline. We have our application that is running on the CPU. All these vertex assembly, vertex operation, vertex processing, primitive assembly, primitive operations, rasterization, and fragment level operations, the forward rendering pipeline, this order, this cascade of operations are run on the GPU in a parallel manner. So usually the data flow is like this. The user program, as I said, is running on the CPU. So we will have an application program that runs on the CPU, which is, for example, capturing user input, interaction with the user, interaction with the operating system, with the frame buffer, everything. So we have the user program running on the CPU. And via the bus, the data is sent to the GPU. We don't want to use this bus a lot at every frame. For example, usually what we do is, if you have a really large virtual scene with thousands of vertices and with really high detailed textures, megapixels of textures, for example, you send them at the beginning of your, so you have an initialization stage in which you send some data, you copy some data to the GPU. Like, for example, all of your vertex geometry data, you can push them onto the GPU initially. We'll have function calls for that. I'm going to show you those function calls. And after that, at every frame, during animation or during the application, for example, we just send certain state information. Like if the certain models change their locations, we just need to send a 4x4 matrix. Which shows how the transformation, to show those transformations, how they're changed. If certain objects change their positions, it's just actually applying a transformation matrix to them. Or we can send some values at every time frame. Some of those data may be vertex specific. Some of them may be like global variables that will apply to every one of the vertices in our scene. These are called uniform variables. And there are also attributes. So we either send some uniform values like a transformation matrix or a projection transformation matrix that is going to be applicable to all of the models, all of the vertices in your scene. Or we may sometimes send vertex level attributes also at every level. So this could be done with communication between the CPU and the GPU. And on the GPU, the geometry is processed, the vertex processing done, fragment processing is done, and then GPU talks directly your graphics card when these drivers are installed. They are able to talk with your frame buffer directly through these drivers. And GPU writes the results on the frame buffer. Sometimes it may write it onto a texture on its own memory. We can sometimes do off-screen rendering. But if we say that it's going to be written onto the display, onto the monitor, but with the help of these drivers, different communication protocols, the frame buffer is written onto the monitor as a displayed image. So the user program is an OpenGL program. I'm going to show you an example, and it's going to be running on the CPU. We are going to compile it and run it on the CPU, either from the command line on Windows or from a shell prompt from a terminal window on Ubuntu or Mac OS X. Initially, all of them is in the main system. All the data is in the main system memory. When you load them, when you read a file which contains your virtual scene, your scene information, it's first on the disk, then you read them, and it's on the main memory. The user program is responsible to arbitrate this overall flow and send data to the GPU, open a window, manage user interaction, decide what to draw, when to draw, things like these. And also, we can install these specific programs. Since our GPUs are programmable, we can ask the GPU to compile these shaders, these small programs that run on the GPU. They're called shaders. And in this course, we're going to learn how to write vertex shaders and fragment shaders. They are compiled and run. We don't have an executable which is pre-compiled here. The thing is that these shaders, we just have a text you don't need to recompile your CPU program if you make changes, for example, on this GPU program in a notepad, because what the CPU program does is that it reads that file in runtime, it sends that file, it compiles and sends the compiled file to the GPU and have the GPU run it on itself. So we're going to show you examples on these, and I think it's going to be more clear if instead of talking about it abstractly like this, seeing them in action will be really helpful. Now, so OpenGL by itself just deals with the graphics part, which is the three-dimensional graphics part where we have a virtual scene, the vertices. So OpenGL is actually just dealing with the stuff you have written up to now in your ray tracing programs or software rasterizer that you're writing in your second assignment. In those assignments, if what you do is you also don't deal with any window management, right? Because you just write your output to a ppm file. So in that regard, what you're writing, whatever you have in your code, is similar to what OpenGL provides. OpenGL does not provide how a graphics contains is going to be obtained in the frame buffer as a separate window on your machine. So it's not a window management library. It just focuses on the 3D graphics rendering part. It doesn't deal with mouse keyboard interactions at all. So it's just the part that you have written in the first two assignments. Because these window management, each operating system has a different mechanism. OpenGL is more like a platform-independent graphics API, which does not want to deal with these window management-related issues. But there are some other high-level APIs that allows us that when we use them alongside with OpenGL, we are able to also get ourselves a window, pop up a window, run it full screen, for example, and then have OpenGL draw things on this graphics context. So we updated the slides from last year's slides to have this our new library that we've been using in the last 3-4 years, GLFW. Before that, we were using a library called GLUT, G-L-U-T. So GLUT is a very lightweight library, but it's really old. It's not maintained anymore. And GLFW is a more modern API, and it's maintained. It has a nice web page that you can, I think, for example, I think we have it here. So this is there's a guide. So glfw.org, the website is glfw.org, glfw.org, and this is that window guide thing. But if you go to the main web page, so this is how it looks like. So you can download. You can. I think it's open source. Yeah, it's an open source multi-platform library for OpenGL. OpenGL ES. ES stands for embedded systems. So OpenGL running on mobile phones, for example, is OpenGL ES. And Vulkan development on the desktop. It provides a simple API for creating windows, context. So this context means graphics context where OpenGL is able to use its viewport. Basically, this context is our viewport. And surfaces receiving input and events. So it can receive, when I say surfaces like the mouse or on a tablet, for example, where you can interact with touch gestures. You can have keyboard input output, mouse input output. It's written in C, and it supports Windows, macOS, X11, and Wayland. So we're going to download. So let me go ahead and download GLFW. I don't have it here on my machine. So, but since we're going to write it, we're going to be using this GLFW in some kind of a C++ development environment. So we have to have ourselves a way to also to compile. First, compile and run C++ programs on your Windows machine. The simplest way to do that, I mean, you may install Visual Studio or other development environments, but very a very simple way to do that, to have a development environment on your Windows machine, is to go ahead and download this code blocks with MinGW. So actually, this GCC, G++, they are actually available on Windows through a library called minimum GNU for Windows. So MinGW. So this MinGW comes with build essentials that you're going to need for on a Windows machine. So one way you can directly get MinGW from MinGW's website, or you can go ahead and go to this code blocks website, in which when you say it's basically an IDE, integrated development environment. When you go ahead and download the binary release, there are different binary releases. So when you click on Windows XP here, there are different setup options, as you can see here. This one is MinGW setup.exe. Comes with MinGW itself, so it's written here. So this one, the code block setup exe file, includes additionally the GCC, G++, G-Fortran compiler, and GDB debugger from this project. So when you install this, I think I have already code blocks installed on my machine. I can take a look at it like this. Windows program files, code blocks. So I have it here. Code blocks. As you can see under code blocks, I have this MinGW, and this MinGW has these libraries. I have to go to this. This is 64-bit, the MinGW, so there is also support 64-bit architecture. If you go to the lib directory of this, you're going to see it looks very much like the lib directory USR lib directory on a Linux machine. Okay, so the libraries are very similarly compiled. They're not DLLs. Usually, when you're developing on a Windows, on a native Windows like this, you usually have DLLs, dynamically linked libraries, that resides in your system folder. But as you can see, we have this lib directory, and there's this include directory. We have lots of header files, which you can, the standard header files are here. And there's a GL directory here, which also comes with MinGW. So you don't need to install OpenGL. So MinGW contains OpenGL header files. But if you look at this, yeah, there is GL, GLU, some I don't know what this GL extension libraries, but for these extension libraries, I think we could use these too, but we are going to use a different extension library called glue. That's another library that we'll need. And the reason, so why is GLFW not enough? So let's see what glue is about. So glue is the OpenGL extension wrangler library. So why do we need an OpenGL extension? So the default OpenGL API has these basic function calls, but in order to talk with the graphics card with these advanced functions, which are to use them as programmable shaders and programmable graphics cards, in order to compile and install our shaders on them, these functions are actually these functions are not included in the basic OpenGL gl.h. So that's what this glue is about. Maybe, I mean, this one is explaining, it will explain it better than me. Is a cross-platform OpenGL extension loading library. So to load the extension, because this OpenGL graphics API is developed, new functions are coming. So this glue is able to tap in those additional functions that are provided in graphics cards. So it provides efficient runtime mechanisms for determining which OpenGL extensions are supported on the target platform. It's tested on a variety of systems, including Windows, Linux, Mac OS X, and FreeBSD, RX, and Solaris. So here is how these are the two libraries that we're going to use, glue and GLFW. Okay, and as I said, the way to install them on so when you download and install code blocks with MinGW, you're going to have this 64-bit part. So there's also this lib and include directories are here, but these are not these are really not the real include and header files. They are inside this 64x86 64-bit part. So these are our main include and library files are here. So what we need to do is installing this GLFW and glue basically is downloading them. We are going to download precompiled libraries and header files. We are going to put the header files here in include directory and the precompiled libraries in this lib directory, and make sure we link those libraries when we are compiling our OpenGL programs. So that's basically the way to install those. Actually, at this point, we can do that before going into the details of these GLFW functions. But as you can see, the rest of the slides are mostly is an introduction to how we deal with this GLFW library, how we include it in our OpenGL or graphics application source code to open up a window, manage an application, which is basically graphics applications are in such a way that you first do certain initialization tasks, and after some point your program goes into an infinite rendering loop, which is so each application, each graphics application is actually in an infinite loop. Let me show you like this. So this is an infinite loop we have here until the graphics windows close. At each frame, we render our scene. We have certain animation which changes certain parameters of the objects, for example, changing position of the objects or things like that. We do it in this function. So this is what we call the rendering loop. So it runs hopefully about 30 to 60 times per second. At each render scene, we clear the entire frame buffer and draw everything from scratch at every frame. So it's just like monitors everything when certain things happen. For example, if you move this window actually from here to here, as you can see, every time the operating system actually is drawing this frame buffer from scratch. And we are going to use double buffering here again to not see the clearing of the frame buffer before rendering something from scratch at each time. So in your first two assignments, the ppms that you generate refers to just this function. This is your render scene function. You just create this single ppm with a certain resolution in which you are writing it to file. In this render scene function, we are going to do that thing that you in one run of your ray tracer or your software rasterizer. Instead of writing them to ppm files, we are going to write it to the frame buffer in which we are going to see it on our screen. And this is going to happen so fast that we are going to see a smooth animation. So what would I recommend? Actually there is no whether you should run OpenGL in Windows or Linux. If you have a Linux machine which can access the graphics cards, I think Ubuntu is able to do that. You can use your Linux environment. Whatever you're more comfortable. It doesn't matter actually. I wrote some programs even on Mac. It wasn't very difficult. The only thing you have to be careful about is sometimes the libraries that you include, or while you're compiling, the library names may be different. For example, while I'm compiling here, I'm going to link it with -L OpenGL 32, something like that. But on Linux, I'm just going to write -L capital letters GL. So the library names may change, but other than that, whatever environment you're more comfortable in, currently coding, okay, you don't need to change your current comfortable coding environment to something else. If you're currently developing or writing your other courses assignments on Linux by using, for example, Sublime Text or some other, whatever your favorite editor is, you may be using Notepad++ on Windows or Visual Studio or something else. As I said, like I think on Linux the popular IDEs are like Sublime Text, Genie, Code Blocks. These are some IDEs that I know people use. But what I do personally, I mean, it's really it's my own personal preference. Whatever you feel more comfortable, you may do it on that. But what I usually do is when I'm on a Windows machine like this, I write my code on Notepad++. Okay, for example, if you take a look at this test.c, which I'm going to share with you on OpenGL. So this is my Notepad++ with, you can change the preferences settings to have different styles. So I have this dark style, but I mean, you may use other things. But there's nice syntax highlighting. As you can see, installing glue means that we have to put, right now if I'm going to compile this program, this is not going to run compiled, because if you look at the include directory under GL here, I don't have glue. I don't have glue installed yet. Also, do I have GLFW? No. If you look at here, I don't have GLFW. So I need to install glue and GLFW on my machine. I'm going to show that to you in the second hour. And I'm using this additional header file here, which contains some nice matrix linmath library. I think it contains some matrix functions. Let's see, it's a 13 kilobytes header file. Includes math.h, so it can have, for example, vector3, multiply, cross product, reflection of a vector, vector4, cross product, reflection of a vector. Oh, it has math 4x4, math 4x4, duplicate, row-wise, column, row, transpose, add, subtract. So it has these matrix operations. Scale, it has scale, multiply two matrices, it has matrix multiplication, multiplying a matrix with a vector, translate in place, rotate, all these rotate functions. Look at this. This is sine, cosine. This is my u vector. It's, I think, for normalization or something. Yeah, it normalizes it and then it multiplies. So it sets up this S matrix and then it does rotation around x-axis, rotation around y-axis, z-axis, inverting a matrix. So it has nice function calls. Like even you can make up your orthographic projection matrix by just these. Look at this: L, R, B, T, N, and F. You know these values, right? L, R, B, T, N, F. You're very familiar with these variable names in this course. So it can make up this orthographic projection matrix for you. Perspective matrix, field of view in the y-axis, the aspect ratio, which means aspect times this will give you the field of view in the x-axis, and near and far planes. Look at function. This is the camera transformation. Some of these functions are very common in OpenGL, but we are not going to be using OpenGL libraries directly. Actually, many of these functions like GL rotate, GL translate, there were OpenGL functions to change your current model view matrix on the fly inside the OpenGL. But these days, graphics programming is getting more and more lower level. It gives more power to the user. The user has to deal with all these things on her own because they are now some of these functions like GL rotate, GL translate, they're obsolete. OpenGL programs do not use them anymore. So that's what linmath is used for. And this is a very simple program we are going to see on, although it's 150 lines of code. But if you look at this, what it does is the first part, oh, by the way, it's using some vertex and fragment shaders. Let's see how they're done. But here's the initialization part. Plus of all these, you can get this test code and use it as a template to develop your own code. But let's have a 10-minute break now before we continue on this. In order to see what this does, after the break, I'm going to download and install this GLFW and glue on my own machine and try to compile and run this. Oh, by the way, look at this. This is the, in this code, you see a string, a constant character. It's string, which is like a code. Okay, so this is our code that we are going to compile and install on the GPU. Is just a text for this program. It's hard coded, as you can see. It could have been written in a file, but if it was in a file, this is what we would do. We would read from the file, text line by line, make this long string, and then call some functions to compile the string and link it and install it on the GPU. So we are going to see what these are after the break. Okay, let's have a 10-minute break until 10:48, and after the break we will continue. I will stop recording now.